Hello. In this segment, we're going to be talking about assembly language. Assembly language is one step above machine code and is the lowest level language that humans can actually read and write. Let's talk about some generations of languages. The first generation languages were programmed directly in binary into the computer system on which they would execute. So this computer, for example, the Altair 8800, was programmed directly with switches on the front. So the programmer would have to figure out what the machine code was for the instruction he wanted to execute, set the switches independently, and then press a button to store the instruction into memory. This was a very difficult way to program computer systems. So a second generation of languages called assembly languages emerged. In assembly language, humans could read and write these languages with a little bit of difficulty. So instead of programming directly in binary, the programmer could understand a load instruction, or an add instruction, or a store instruction, or a branch instruction. But these languages were then run through a separate program called an assembler that produced as output the machine code that would execute on the machine. The third generation of programming languages were high-level languages, and these are the ones that we mostly think about when we think about programming. So these include things like while loops and if-then-else structures and functions and so on. And most programming languages today, including those that are object-oriented, are third-generation languages. There were efforts in the 1990s and the early 2000s to have a fourth generation of programming languages that use natural language or non-procedural languages or visual programming for report generation and so on. And these programs then generated other programs that were compiled and run on the computer. But that experiment was not particularly successful, and those are in limited use today, mostly in report generators for databases. The key idea, though, is that regardless of the language of writing, computers only execute machine code, binary ones and zeros. All non-machine code is going to go through a translation phase into machine code. So second-generation assemblers will run through an assembler to produce machine code. Third-generation programming languages will run through a compiler to produce machine code, and so on. So the question is, if we're used to programming in high-level language constructs like while loops and if statements, how does the code on the left become the code on the right that the machine can execute directly? And so let's walk through an example of translating this code by hand so that we can understand the process. So the first thing that we'll do is we'll take the high-level language code and we'll convert it into a pseudocode language that I'll call if-goto. So these are the only two control structures we have in if-goto. We can ask, if a condition is met, then go to another location. And of course, we also have an unconditional goto. So here's the code translated. Notice that the variable assignments of I, j, and k are all the same. And now we've converted the while loop into an if-goto statement. I have to convert the condition, while k is less than 10, into a condition where I would not want to execute the loop. So I'll invert that condition. If k minus 10 is equal to 0, then I can skip over the body of the loop. Otherwise, I do all the assignments inside the loop, and at the very bottom, I go back to the top of the loop. Of course, if the condition is met, then I'll jump all the way down to the bottom where I will halt. And so loop and done are labels that are used for branch targets. Branching is where we change the program counter in the computer to go to a new location. Once we have the high-level pseudocode of if-goto, we can translate that directly into assembly language. And this is assembly language here is what we would see in the little man computer. So the statement, if k minus 10 is equal to 0, go to done, translates into load k into the accumulator, subtract 10 from the accumulator, and if that result is 0, branch to done. If we don't branch to done, then I'll execute the internals of the loop. So to compute fib equal I plus j, I would load I into the accumulator, add j into the accumulator, and then store the result at fib. Likewise, a simple assignment is load j, then store I, load fib, then store j, and of course then I can load I and print out the result through the out statement. To increment a variable, I load k, I add 1, and I store the result back into k. Once I reach the bottom of the loop, I have to test to see if the loop will execute again. So I have an unconditional branch back up to the very top of the program, and at the top of the program we will test the condition again. If the condition is met, it will skip to the bottom again. So it goes up to the top and then back to the bottom when the condition is met. Of course, we also have our data section where we have some initial values for j, I, k, fib, 10, and 1. Once we have this translated into the little man instruction set, we can assemble these instructions into machine code by using our lookup table for our opcodes and looking at our table of where variables are stored to get our mailbox addresses. So, this is the same program, and in the table what we see is the machine code representation for the little man computer. So, in box 1, I have code 520. This is equivalent to loading k. 5 is the load instruction, 20 is the mailbox that contains the value of k. Then we have a subtract 10. 2 is the subtract opcode, and 22 is the location of the number 10 in memory. We can then have a branch instruction, opcode 7, to done, which is at location 17, so we can see that all the way down here at the bottom. And at the 17 location, we have the halt instruction. And so on. We would hand assemble all of these things to get the machine code for the little man computer. Of course, we also have our data statements, so we have J in box 18, I in box 19, K in box 20, and so on. In summary, high-level languages are convenient for us to read and write as humans, but computers only execute binary machine code. So any language other than machine code needs to go through a translation process. Compilers translate high-level languages, third-generation languages, into machine code, whereas assemblers translate assembly languages into machine code. For us as humans, we can use the if-go-to pseudocode as an intermediate language between the high-level language that we normally read and write and the assembler language that we're going to be forced to write and run through an assembler.